Whenever I manage to find a moment to pause and look up at the stars, I often wonder, are we alone? The answer to one of life's greatest mysteries may lie below the ice of Europa. Europa is one of the many moons that we know of which is orbiting around Jupiter. Current estimates suggest that the icy moon formed around 4.5 billion years ago, close to the same age as Earth, in which current calculations put it around 4.54 billion years old. This should be a sufficient amount of time for complex life to evolve in the ocean below the icy surface under the proper conditions. At first glance, the idea of an ocean existing on an icy moon seems implausible. Europa is roughly 500 million miles away from the Sun, or about 5.2 astronomical units. One astronomical unit is the distance of Earth from the Sun, which puts Europa far past our solar system's habitable zone. The energy necessary to sustain the ocean has to be coming from somewhere other than the Sun. The most probable energy source is from the tidal heating caused by the moon orbiting Jupiter. Jupiter's other moon, Io, is a great example of the amount of energy tidal heating can produce. Io has hundreds of volcanoes and is the most volcanically active celestial object in the solar system. Almost all of the volcanism on Io originates from tidal heating. Europa and Io are tidally locked to Jupiter, which means the same side of the moon is facing the planet at all times. Due to its slightly elliptical orbit around Jupiter, one side of Europa is pulled more towards the planet than the other. When the moon is closest to the planet during its orbit, the moon begins to stretch towards the planet. Then, as the moon moves further away, the moon relaxes until Europa moves closer to the planet again. After repeated cycles of stretching and contracting, the energy is dissipated as heat in the moon's inner core. This provides a sufficient heat source to produce geological activity inside of the moon. Geological activity could then create hydrothermal vents on the seafloor and would be partly responsible for heating and melting the lower layer of ice. The ocean created from melting the lower layer of ice would then produce more heat due to tidal friction. Jupiter's gravity would have a similar effect on the ocean as it does with the moon's inner core. It would cause the ocean to flex and bulge, which would lead to the energy being dissipated as heat. On Earth, barotropic and baroclinic tides are generated due to the influence of gravitational forces from the moon and, to some extent, the sun. Barotropic tides would generate heat through frictional dissipation between the icy crust and the seafloor. Baroclinic tides generate heat by internal wave breaking. Internal waves would propagate throughout the ocean and then break when met with water with different densities affected by temperature and salinity differences. Baroclinic tides would significantly contribute to vertical mixing of the ocean. This would help with redistributing heat and nutrients. Tides generate large amounts of energy on Earth and would likely generate far more on Europa due to Jupiter's immense gravitational influence on the moon. This would produce a positive feedback loop in which the ice being melted causes even more ice to melt, eventually reaching an equilibrium between the extreme cold of space that freezes the top layer of water and the ocean below the ice. The average surface temperature on Europa is negative 260 degrees Fahrenheit at the equator and negative 370 degrees Fahrenheit at the poles. So a person would need more than just a jacket to stay warm. Europa is one of the few moons in the solar system with an atmosphere. However, the atmosphere is thin and mainly made of oxygen and water vapor. The Hubble Space Telescope captured cryovolcanic activity on Europa in what appears to be plumes of water vapor being shot out into space. But due to Europa's size and gravitational influence, much of these plumes settle back down onto the surface. These plumes of vapor are estimated to reach heights of over 100 miles high, showcasing the effect that tidal heating has on Europa. These cryovolcanoes may be partially responsible for the reddish-brown material found across the surface of Europa, which could be a sign that the ocean is in contact with the rocky surface of the moon. This would increase the likelihood that there may be life below the icy surface. Spectrographic studies suggest that these formations contain salts and possibly organic compounds. Conducting a spectrographic analysis means examining the way light affects a certain material. and many materials reflect a distinct spectrum of light, almost like a fingerprint. This allows astronomers to get a rough idea of what may be on the surface of the moon. Jupiter has one of the strongest magnetic fields out of all the planets in the solar system. This helped astronomers to get a hint of what may be below the moon's surface. NASA launched the Galileo mission in 1989, whose primary objective was to observe the 4 Galilean moons, Io, Europa, Ganymede, and Callisto, orbiting around Jupiter. The spacecraft reached Jupiter's orbit in 1995 and made some exciting discoveries about Europa. One of which is that Jupiter's magnetic field was being disrupted around Europa. The implications of this suggest that there is a magnetic field being created within Europa. However, the induced magnetic field is probably not coming from the mantle, but above the rocky surface, implying that there must be some electrically conductive fluid beneath the icy surface. Based on Europa's composition, it is highly probable that the induced magnetic field is coming from a global ocean of salty water. Because of Jupiter's strong magnetic field, it is a powerful particle accelerator. Europa is bombarded with ionizing radiation because of Jupiter's magnetic field. The amount of radiation that Europa is subjected to is equal to 5.4 sieverts. This would kill a human in 24 hours if they were to land on the moon. So it's probably a good idea to not book an in-person winter wonderland trip with the family on Europa just yet. Many of these particles that hit Europa's surface may cause reactions to occur through radiolysis. Radiolysis is the dissociation of molecules by ionizing radiation. This could be a promising mechanism for how the ocean below the icy surface can become oxygenated. Ionizing radiation could split the water molecules on the surface and allow for oxygen molecules and hydrogen peroxide to eventually seep into the ocean below. Oxygen molecules and hydrogen peroxide could dissolve into the ice. When hydrogen peroxide is mixed with liquid water, it produces water and oxygen gas. Estimates suggest that the ice crust may be around 10 to 15 miles thick. Due to the effects of tidal friction and warming from the ocean below, the ice crust may experience convection currents similar to the Earth's mantle. The evidence for this is due to the surface only being approximately 40 to 90 million years old, despite the moon being billions of years old. The age of the icy crust is determined by the amount of impact craters on the surface. Based on Europa's statistical likelihood of being hit by an asteroid, it is highly probable that the surface is actually young in geological terms, which would indicate that the surface is being renewed over time. Convection currents and subduction of the crust may drive the cold, dense, oxygenated ice and minerals from the surface to the ocean below. Then warm, lower density ice may rise to the top and contribute to bringing minerals from the ocean to the surface. This would lead to the ocean possibly becoming as oxygenated as the Earth's oceans, making it suitable for complex life to evolve. If the ocean is in contact with the sea floor, then there could be life near the hydrothermal vents that would have been made from the geological activity within the moon's core. These vents would release energy and minerals that could be suitable for life to evolve. Similar to how deep-sea vents on Earth may have been cradles for primordial life. These vents would allow for abiotic processes to occur, meaning oxygen would not be necessary and primordial life could evolve utilizing sulfur, methane, and iron as a fuel source to metabolize nutrients. Bacteria would take advantage of the heat and minerals released from these vents and multiply, eventually creating mats of bacteria covering these vents and the surrounding surfaces, allowing for more complex life to evolve that feeds off of the bacteria. However, the life on Europa would have potentially quite different biochemistry than what is seen on Earth. Deep-sea fish require certain compounds in their blood in order to protect themselves from the immense pressure of living miles below the surface. Trimethylamine N-oxide, or TMAO, is used across species in the deep sea to prevent biomolecular structures from destabilizing. Without compounds such as TMAO, The blood and muscles of deep-sea fish would compress to the point that would make it either extremely hard or impossible for chemical reactions that support life to occur. Typically, the deeper a fish lives in the ocean, the higher the concentration of TMAO in their blood. The deepest point in the ocean that life has been found on Earth is in the Challenger Deep. The Challenger Deep is approximately 6.8 miles deep. A polychaete, sea cucumber, and shrimp have been spotted in the depths of the Challenger Deep. So it is possible for complex life to survive in these extreme depths. But the ocean environment is far more extreme on Europa. Despite Europa being around 1/4 the size of Earth, it may have an ocean with twice as much water as Earth's ocean. The ocean on Europa is estimated to be around 40 to 100 miles deep. It may be possible that some deep-sea creatures on Europa evolved to utilize TMAO to endure the immense pressure. TMAO metabolizes into trimethylamine, which is also responsible for the fishy smell from fish. So if there are fish on Europa that use TMAO, then they probably smell really fishy. Due to the extreme depths of Europa's ocean, the deep-sea creatures probably utilize new biochemical processes that have not been discovered yet. Certain traits may have evolved again on Europa which may resemble what is seen on Earth, such as bioluminescence. It is currently believed that bioluminescence has independently evolved approximately dozens of times on Earth. If there is complex life in Europa's ocean, then there is a good chance we can expect to find creatures that produce light. But for now, complex life existing below the icy surface is still up for debate. We won't know for certain what lies below the ice until space exploration missions are launched to examine Europa. There are currently 2 missions set to investigate Europa. Europa Clipper was launched by NASA using a SpaceX Falcon Heavy rocket on October 14, 2024, and will reach Jupiter in 2030. The objectives for this mission will be to conduct a detailed reconnaissance of Europa's ice shell and possible subsurface ocean. Also, to try and determine the thickness of the ice, the depth and salinity of the ocean, and search for potential plumes of water erupting from the surface. As well as assess the moon's habitability by analyzing the surface composition and searching for signs of recent or ongoing geological activity. If Europa Clipper manages to fly inside of a water plume, then it may be possible to analyze the water for traces of microbial life. The Jupiter Icy Moons Explorer, or JUICE, was launched by the ESA in April 2023 and will reach Jupiter in 2031. The objectives for this mission will be to conduct detailed studies of Jupiter and 3 of its largest moons, Ganymede, Callisto, and Europa. It will perform 2 flybys of Europa to study its icy crust, surface composition, and potential subsurface ocean. There has also been a proposed future mission, which would launch a lander on Europa to sample its surface. These missions have the chance to make monumental discoveries that will advance our understanding of the universe. The cultural impact these discoveries may have on humanity would change how we view the universe for the rest of human history. If even microbial life is discovered on Europa, then it would set a precedent that gas giants may have their own quasi-habitability zone. Typically, when the possibility of life existing on another world is hypothesized, it is assumed that the planet needs to be in the habitability zone of a solar system to be able to support life. But if life is found below the ice of Europa, then it would prove that liquid water on the surface of an alien world may not be necessary for life to evolve. Finding life on multiple worlds in one solar system may give more credibility to the idea that life may not be a rare phenomenon in the universe. There are approximately 10 to the 23 stars in the universe. That is a 1 followed by 23 zeros, and this is likely an underestimation. Each star probably has at least one planet orbiting it, with the possibility of even more moons orbiting these planets. If life could evolve even within a quasi-habitability zone, then the concept of us being alone in the universe seems to be implausible. Humanity may be in the midst of a cultural paradigm shift from having a Gaia-centric view of the universe, in which the Earth is seen as the only planet capable of harboring life, to understanding that we may be living through the Amplivitagenic age of the cosmos. That the cosmos is more than capable of generating and supporting vast amounts of life all throughout the universe. Humanity going through such a drastic change in how we view the universe would be somewhat similar to the time when we shifted from having a geocentric to heliocentric view of the universe. Not too long ago, many cultures believed that the Earth was the center of the cosmos and all other celestial bodies orbited around Earth. It is thought that Aristarchus of Samos may have been the first person to push forward the hypothesis of a heliocentric model. Aristarchus was an ancient Greek astronomer who lived from 310 to 230 BC, and may have been inspired by the work of Philolaus. Philolaus was a Greek philosopher who lived from 470 to 385 BC, and is credited with the earliest discussion of the concept of a universal fire in which everything revolved around. But Philolaus thought our sun also revolved around this central fire. Aristarchus was the one who placed the sun at the center of the universe, with the planets orbiting around it. However, the only evidence of his claims is from a book written by Archimedes who referenced his work. The original work of Aristarchus postulating the heliocentric model may have been lost to history. The heliocentric model did not gain widespread prominence until Nicholas Copernicus popularized it when he published his work on the revolutions of the heavenly spheres before his death in 1534 AD. The model was not fully accepted until other scholars such as Galileo Galilei, Johannes Kepler, and Isaac Newton made their own discoveries using telescopes and mathematics to prove that the sun was at the center of the solar system, and all the other planets orbited around it. But over the course of history, it was later proven that the sun is not the center of the universe. Humanity is currently going through a cultural transition, and we may soon prove that our beautiful, life-bearing world is actually just one of many in the vast expanse of the universe. The first team of scientists to find life beyond Earth may have their discovery remembered all throughout history, along with the likes of Galileo Galilei, Johannes Kepler, and Isaac Newton. Not only will the team of scientists be remembered, but also the first government administration that is responsible for finding alien life as well. And who knows, maybe one day, we may come across an alien probe that was sent to communicate with an advanced civilization. Similar to what NASA did with Voyager 1 and 2. They were inspired by the launches of Pioneers 10 and 11, in which both carried small metal plaques identifying their time and place of origin for any space traveler that finds them. The launches of Voyager 1 and 2 were more ambitious, with both of them carrying a message similar to a time capsule. The message is carried by a golden phonograph record. This gold-plated copper disc contains sounds and images that portray the diversity of life and culture on Earth. The record includes greetings in 55 ancient and modern languages. Also a diversity of natural sounds, including those made by surf, thunder, wind, and animals such as birds and whales, with the sole purpose of communicating to an advanced civilization that may come across the Voyager probe. The probe that we come across may be more advanced. An alien civilization may send a probe with an artificial intelligence on board. The AI would probably be the summation of that civilization's culture and might teach whoever finds the probe what life is like on their planet. I have a feeling that whenever I look up at the stars on a cool, crisp night and wonder, are we alone? That there is most likely someone out there in a far distant world looking at the same stars, asking themselves the very same question. If you want to keep exploring the universe together, feel free to subscribe and click that bell notification so you know when new videos are uploaded. Be safe out there.